Hello and welcome back to the channel. I hope that you're all safe from COVID-19 and you're starting to get back to normal in terms of your daily life and mental health and all of those things. So in this lecture we're going to be talking about the first circuit analysis method, which is nodal analysis, and this is essentially the formalized version of Kirchhoff's current law. We're going to be looking at some examples and talk about supernodes after we look at the basic nodal analysis examples, and also we're going to take a quiz as usual. And to be able to understand this lecture and get the most out of it, you should be by now familiar with Ohm's law, current, voltage, and power relationships, determining the equivalent resistance in resistive networks, KCL and KVL, Kirchhoff's laws, and the linear algebra fundamentals, which we saw in the previous lecture. If you'd like to follow along with LT Spice or other circuit simulators of your choice, that'd be a very good thing to do to maximize or optimize your learning experience. Okay, so the approach for nodal analysis is to essentially apply Kirchhoff's current law by first selecting a reference or ground node for the circuit and applying KCL to every non-reference branch. And if you recall from earlier lectures, the benefit of this is that by selecting a ground node, what that allows us to do is to put one of our probes, if you want to talk about this in a practical sense, we can put our digital multimeters probes, the black or negative one, to ground, and use the positive probe or red probe to go around the circuit and measure the voltage of any given node with respect to the ground node. And so sometimes you have to keep in mind that the ground node is going to be implicit. So we're going to have a ground sign anywhere in our circuit, and it's going to be implicit. Any voltage given in the circuit is going to be implicitly referenced to ground, and so we need to keep that in mind. And if you ever see a voltage value, we need to always know that voltage is relative, so there's no absolute sense. It doesn't mean anything to say a voltage at a given point in space is a certain amount. It's always relative to another point in space. So keeping that in mind, what we're going to do then is, after applying KCL to all the non-reference nodes, we're going to make a system of equations and basically review our algebra and make sure that we're very comfortable putting those variables into matrices, and then plugging those into our favorite matrix solver, in my case MATLAB or Matrix Laboratory, and quickly solving these circuit problems. Remember that this is not a math class and this is not a physics class, and as electrical engineers we need to be able to utilize those tools to our advantage and quickly solve engineering problems, and that is what we're going to be doing. Now also, for now, we're not going to be using any voltages in our circuits, voltage sources in our circuits, because if you recall, an ideal voltage source only guarantees a certain voltage across its terminals. The current through it could be anything that will allow it to produce the desired voltage. And so you can see how that could be a problem in a method where Kirchhoff's current law is used. If that voltage source, that ideal voltage source, is anywhere in between two nodes, that's going to be called a supernode, and we will deal with that later in this video. Okay, let's go ahead and do the first example, but prior to doing so, let's review what an ideal current source is. So if we look at an ideal current source, what it does is it will supply you a specified current no matter what the terminal voltages are. So if I have the plus and minus terminals as such, the IV characteristic, which is a very important concept for electrical engineers and for this field, is that we look at either current in the vertical axis and voltage in the horizontal axis, or vice versa. Usually for transistors and those kinds of analog design, you'll see current in the vertical axis. So I'll say I here and V here. What you would expect an ideal current source to do is to provide you a particular current no matter what the voltage across it is. You can see it's flat over voltage. In reality, this is not it's not practical. You can get current sources and voltage sources that are very close to ideal, but usually don't get a very flat response like that. And so having reviewed this, let's go ahead and look at the first example. We'd like to be able to use nodal analysis to find out the current through R1. This is a very simple example as a starter, and so what we can do first is indicate the direction of current flow into that node of interest. And what I've done is I've kind of followed what we expect to happen. We have a current source pushing current in this direction, and another one pushing it to the left direction here. And so what we expect is that the current essentially sums up at this node and flows down to the resistor. And so, as I said, this is a very trivial example just as a warm-up. And in summary, what we would say is that the node voltage V1 there is going to be the sum of the two currents multiplied by the resistance. Very simple example. That is going to give us our node voltage. Now moving on to another example, which is also somewhat trivial, but it highlights an important point, which is the practicality of building these ideal sources. So one question that you might run into is what would happen if I have two ideal sources connected in series. So if I have designed some sort of an ideal source, current source somehow to give me 1 amp and another one to give me 2 amps, what would happen if I connect them in series? Of course, on paper, this will cause a collision of some sort of contradiction in theory, and so your model breaks. But in reality, what happens is this. So don't worry too much about these transistors here and what's going on, but the idea is that I essentially sized up these transistors to provide me 1 amp in this branch and 2 amps in this other branch. And the first scenario is the following. I have VDD, the voltage drain, which is used for transistors, terminology for transistors, MOSFETs and bipolar junction transistors, which is beyond the scope of this particular lecture series. So I have some sort of supply voltage essentially with respect to ground, and I have two different ideal current sources, and these are modeled here by some transistors and some current mirroring, which is again beyond the scope of this class. The point to consider is the following, which is that the current through the first branch is 1 amp and the second branch is 2 amps. Now what happens if I combine these two different sources? Now this design is not necessarily the best current source design, but it illustrates the point. So if I actually connect these two together as shown above, the 1 amp and the 2 amp source, what would actually happen is that you will still get, it will collapse down to one of these currents. So in this case the 1 amp source dominates, and what would happen is that the transistor would then, the transistor of the other current source, in this case the 2 amp source, what it does is it goes out of saturation. And that's a terminology for analog design and transistors, which we're not going to get into right now. But what that means is one of these guys succumbs to the pressure, and basically, as you can see, the current through the first guy, M1, is 1 amp, and the current through the third transistor here is 0.9999, very close to 1 amp. And so, whereas previously this guy, M3, was giving us 2 amps. And so that's the point of, I just wanted to highlight this because at some point you're going to probably ask yourself this question of what happens if I connect these ideal sources together. And remember, for a voltage source, what happens if I connect two ideal voltage sources in parallel? Well, the same kind of idea would apply. One of them would dominate the other. Okay, now let's go ahead and work on a more interesting example and apply all of the techniques we've learned thus far and the points that we learned about nodal analysis, which is to first select a reference node and find the remaining voltages and solve for those voltages or currents. In this case, we care about voltages that are unknown at these two individual nodes, and what we're going to do is we're going to apply KCL in a very methodical manner, which is called the nodal analysis. And if you watch lecture 9, the expectation is that you will choose your favorite matrix method to solve the equations that arise from this system. So regardless of what method you choose, whether it's Cramer's rule or inversion or just plug it into a calculator or matrix solver, you're still going to need to know how to arrive at those equations that govern a given system. And the way we do that is we apply some sort of physical law to find out the interplay between these currents and voltages. And so let's dive right in. So the first thing I'm going to do is assume some directions for current flow. Now it doesn't matter what direction you choose so long as you're consistent within the picture you've painted. So what do I mean by that? So if I choose I1 to be flowing into this branch, which is kind of a logical choice, but again doesn't matter which direction you choose. If I say it's going this way and then I have some current I2 going the same direction as the current source indicates, some current going this way through R2 and some current going here, now I cannot then choose a current here that is opposing the current that flows through R2. Now you might ask yourself, why is it that the direction doesn't matter, and as long as you keep it consistent things will work out correctly? The reason is that 0 exists, and if you can factor out a -1 from one side of the equation and there's a 0 on the other side, you can essentially factor out that -1 and cancel it out by dividing both sides by -1. And so that's kind of just a special property that we're not going to get into because it's more mathematical than and it's not the subject of discussion here. So having indicated directions on the circuit for us to keep ourselves on the right track, we can now go ahead and write equations for each of the currents. Okay, so let's begin actually finding the equations that we're going to plug into the matrices for this particular system. So the first equation is going to be describing all the currents going into the first node, and so we're indicating that I1 is flowing into the node and the rest of the currents are flowing out. And so if you've seen the previous lectures, you would know that what we can do is essentially say this current from I1 is equal to all the other currents summed up with each other. And if you don't see that immediately, I would advise you to go back and try some example problems where you apply KCL and find that you can do that simplification easily. So by doing that, we obtain I1 is equal to V1 over R1 plus V1 minus V2 over R2 plus I2. So these are all the currents that are leaving that branch. So V1 over R1 is this current going this way, and the reason we can do that is because we've grounded one of the nodes to reference node, and so we can say V1 over R1 because that the voltage across R1 is V1 with respect to ground. So V1 over R1 plus V1 minus V2, that's the voltage across R2, and dividing by resistance gives you the current, and I2 is simply this ideal current source. Moving on to the second node, we can start with I2, and we're seeing that I've predicted that I2 is going to go this way, current through R2 is going to flow this way, and they're going to sum up to the third current down there, V2 over R3. And so summing those up, we can see that this current is going to be equal to the sum of those currents, and so V2 over R3 is going to be equal to I2 plus V1 minus V2 over R2. So now that we have our two systems of equations, we have to identify our variables and knowns. So in this case, we can see that we have a bunch of resistors and voltages and currents. The currents are going to be given. We're going to know you can design the problem in such a way that voltage is given and current is not, but that should be trivial. The point is to find the voltages for nodal analysis. And so I is going to be known, so let me indicate that in this way, and the resistance values are going to be known, and so the unknowns are going to be V1 and V2 in this case. So we have two unknowns and two equations, so we should be able to correctly solve that problem. So let's go ahead and move on to placing these into the matrix. So before doing any of that and solving the matrix by your method of your favorite method, what we have to do is get it into the right format. So the format is you want to get all of your sources into one side and all your variables on the other side. So I2 is one of the source terms, the current from a current source. and I'm going to subtract it to the other side. So number 1 is going to be modified in this manner, and I'm going to simplify things to where it's some coefficient times the variable 1 and some coefficient times variable 2. In other words, if I have a negative number, I'm going to make sure that's a positive here, but then lump that negative into the coefficient. Just a very simple algebraic trick, no big deal. So there's a 1 over R1 here and a 1 over R2 here. To make our lives a little bit easier, what we can do is say, okay, conductance from previous lectures is 1 over resistance. So anytime I see, for example, 1 over R1, I can just say that's a G1. So I'll do that here. So 1 over R1 plus 1 over R2 is going to multiply by V1. So I can say G1 plus G2. If you don't recall this, go back to the previous lectures where we talked about resistance and conductance, and it is a very simple concept. So if you just follow algebraic substitution, this is very simple. So looking at the second one, for V2 we have a minus sign, so minus 1 over R2. So in that case that's negative G2. And for the second equation, I'm going to take everybody here on the other side to keep I2 positive. Either way should work, but that's just preference. So in this case, what do we have? V2 over R3 minus, or minus a minus is a positive. So for V2 at least, I know we will have G2 plus G3. So G2 plus G3 times V2. And for the first one, we're going to have a negative 1 over R2, which is a negative G2 times a V1. So having put everything into this form, now we can rewrite the equation and place it into a matrix. So we can have I1 minus I2 on the first row, and on the second row we'll have I2. So this is a 2 by 1 matrix, which is basically a vector, and this vector is composed of the currents in this system. Now that is going to be equal to, here is where we do the matrix multiplication. So I'm going to have a matrix and call it the conductance matrix of the system. And so that's going to be, we'll see the format in a second. Let me go ahead and fill it out. So G1 plus G2 minus G2 minus G2 and G2 plus G3 multiplied by V1, V2. Okay, so you can see I can recreate this conditions row by row. If I have that first equation is put into this first row here, multiplied by V1 and V2. You can see I1 minus I2, that's easy, is equal to G1 plus G2 times the first term, in this case, plus minus G2 times V2, which is what's going on up there, and so on and so forth for the second equation. So what we are currently looking at is the fundamental issue that we see in linear algebra, which is to solve this problem, which is that you have some matrix transformation applied to some unknown vector, and that results in some known vector column. And so in this case, B would be our current, in this case our known current sources, so we know what B is. We have found our conductance matrix here, and what we need to find is the x hat, or the unknown vectors, which are the voltages here. And so there's multiple methods to do this. You can either use Kramer's rule or matrix inversion, or you can crank out the linear algebra by doing Gaussian elimination manually, which I don't recommend really. What I'm choosing to do here is to use the process of matrix inversion, and the idea is that I take the inverse of A and apply that to the equation AX equals B. And what that does is the inverse of a matrix multiplied by itself gives you the unit, I believe it's called the unit matrix, and that gives us x hat is equal to A inverse times B hat. In this case, the inverse of the conductance matrix times the input sources will give us the solution. And that makes sense because what that means is current is equal to conductance times voltage, and that is the units. So the units actually work out. So let's now remember what the steps are to actually find the inverse of A. To find the inverse of A, we have to first find the cofactor of A. So cofactor of A. Then we have to essentially transpose it, take the transpose of the cofactor, and also find the determinant. And finally, what we can do is use the adjoint and divide by the determinant. So A inverse is going to be the adjoint of A over the determinant, and adjoint is simply the cofactor transposed divided by the determinant. So first let's go ahead and just find the determinant. That should be the easiest one. So determinant is equal to, for a 2 by 2 matrix, it's simply A times B, or sorry, A times D minus C times D. So that's this term, that term, subtracted by these two combined. So that's going to be G1 plus G2 multiplied by G2 plus G3 minus negative G2 squared. And so let's just simplify that. And minus G2 squared. Then the next thing is cofactor. So that is determinant. So cofactor is going to be, if you recall, the way we do this is we look at the index, and if the indexes are equal, you get a positive number. If they're not, you get a negative number as a coefficient. And so so that's just a rule for signs. But then what you have to do is, if you look at 1 1, for example, which is this index, row 1 column 1, you have to cover that entire row and column, and what remains is the element of the cofactor. So what I mean by that is C11, C12, C21, C22. So C11 is going to be when we cover the row and column corresponding with that element, and look at what remains. So if you can imagine just covering with your fingers, or in your mind, if you cover the row and the column of this element, you see that this guy remains, G2 plus G3. And the sign convention is that whatever the indices are, so 1 1, it's going to be negative 1 to the power of the sum of those indices. So negative 1 to the power of 1 plus 1 is going to be a positive number, so that's going to be a positive coefficient multiplied by G2 plus G3. Again, if you don't remember this, you should definitely check out lecture 9, which goes over all of this in detail. So in this case, it's going to be a positive number, so G2 plus G3. And then C1, C2 is going to be when we cover, C12 is going to be when we cover the second element, the first row, second column, which is this guy. So this is what remains, and the indices are 1 plus 2, and so that's a negative, that's an odd number. Negative 1 to an odd number is negative, so it's going to be negative of negative G2, which is positive G2. I'll go ahead and finish the rest of these. So I cover this guy, I get the same thing, and same thing there. So G1 plus G2. That is our cofactor, and then we take the transpose, which is the adjoint of A. So the adjoint of A is going to be when we take the transpose, which is simply, if I take the first column and make it a row, that's going to be the transpose. Let's take the second column and transpose it. Okay, so that gives me the adjoint, and A inverse then is going to be the adjoint divided by the determinant. So I'll just call this the determinant, so I don't have to write all the algebra out. So that's going to be 1 over that times the matrix that you saw just above. So that's going to be the inverse. And then what we can do is multiply that by, what we will do with this is to multiply this guy by the current term. So then, the voltage column vector is going to be A inverse times B, or the current vector. I should say the current vector to make it specific. So the vector of currents you saw earlier. So that would be our final answer. So let's go ahead and actually put some numbers to this for a different problems. Okay, so here's a different network with some numbers here. We know the resistor values and the current source values. So we have to find the voltages V1 and V2 through nodal analysis and the linear algebra techniques that we talked about. The first thing I'm going to do is assign some direction for currents, and this is completely arbitrary so long as we keep the interconnection of nodes consistent. So the current going into them should be consistent with the current coming out of a different node. So I1 I'm going to say is going to be entering this node, and the remaining currents are as such. And so then I'm going to write the equations for them describing the system. I'm going to have I1 entering, and that equals V1 over R1, which is this current, and V1 minus V2 over R2, which is this current. The second equation being V1 minus V2 over R2 is equal to V2 over R3 plus I2. So now we have to simplify the equations a bit to put them into matrix form. So I will again get the sources to one side and factorize the coefficients. So I'll also use the conductance relationship to make it easier. So that's going to be G1 plus G2 times V1 plus minus G2 times V2. And for the second equation, we have I2 is equal to, so I'll take this guy to the other side, and we will have G2 for V1 plus negative, G3 minus G2 and minus G3, essentially minus G2 minus G3. Now, to make our lives easier, we can just go ahead and calculate the conductances to have a numerical matrix that we can manipulate instead of the same kind of symbolic matrices. So that's going to be 1 over 4, G2 is going to be 1 over 8, and G3 is going to be 1 over 10. And of course we know the current, so I'm going to turn this into a matrix, which is going to be I1 and I2. So I1 is 2 amps, I2 is 3 amps. That is equal to G1 plus G2. So we can see here that the entire system is represented here as a matrix equation. And so again, what we need to find is the voltages V1 and V2. And to do that, I've chosen the method of matrix inversion. And so I'm going to invert this matrix by first finding its determinant, its adjoint, which requires finding its cofactor and transposing it. So we will set this up, and for determinant we're going to have the first term times the second term, which is 3/8 times negative 9 over 40 minus the product of the other terms. So that's the answer for the determinant, and now we can find the cofactor. So the cofactor of A would be negative 1/8 times, or not times, for the second term we're gonna cover these two guys and negate that term. Then we're going to also negate the other term and finally get to 3/8. And it looks like for the first term I actually made a mistake. For the first term we should have, when we cover these elements, we get negative 9/40. Now to transpose this, to find the adjoint of A, we would have just transpose this guy, and so let's double check. Right, that's correct. So now we're going to divide by the determinant to find A inverse. Okay, so we found our A inverse, and now what we have to do is basically follow this formula, which is that the voltages are going to be the A inverse multiplied by the current vectors. So the V vector is going to equal V1, V2, which is equal to A minus, which is this guy, multiplied by the current vector 2, 3, and the final answer should be a 2 by 1 matrix, which I'm going to write down as. So this is our final answer, and what that means is that V1 is equal to 12 over 11, which is about 1.09 volts, and V2 is equal to about negative 12.7 volts. So now we're going to verify this with MATLAB and see if we actually did the equation correctly. Now do note that MATLAB is not going to check if we did KCL correctly. All it can do is check to see if the values that we obtained, the matrix equation, if that was done correctly. Because if you made any mistakes up to getting the equation in this form, MATLAB is not going to be able to tell us that. So essentially what that means is really pay attention and make sure that when you put your equation into the matrix form, that every entry is correct. That's the most important part. In reality, in the real world, some sort of matrix solver will do the rest of the problem. Just make sure that you know how to set up the problem and put it into a matrix. So let's go ahead and actually verify this with MATLAB. Okay, so looking at MATLAB, you can see that I've entered the matrix A as what it is on what we found the conductance matrix to be. And so if you're not familiar with MATLAB, this is not going to be a MATLAB tutorial, but I've demonstrated what A is, which is the simplified version of the fractions there, and the current I is the column vector, which is 2 by 1 vector, and is 2 and 3 here. And I found the inverse of A and multiplied the inverse of A by the current vector to find the final answer x. You can see here that the final answer is 1.09 and negative 12.7, which verifies that we did everything after the matrix form correctly. So having verified that we did the matrix algebra correctly, now we have to check whether we performed nodal analysis correctly and actually got the correct equation to then put into the linear algebra form. So to verify that, we're going to have LT-SPICE solve the circuit for us and see if we did everything correctly. And if you look at it, we can see that voltage V1 is 1.09 and voltage V2 is negative 12.7. So indeed we have done everything correctly for this problem. Okay, so let's look at a second example. In this case, we're going to have 3 node voltages to find, and they're going to be V1, V2, and V3. In this case, we expect to have a 3 by 3 matrix to be able to accurately represent the system. In addition to that, we also have a new challenge, which is that we have a dependent current source, which means that the value of the current through this branch depends on another variable. In this case, we have 4Ix flowing through this branch, and that current Ix is the current that flows through R1. So if the R1 current increases, so does the current through this branch. So we're going to see how to handle a problem where not only do we have a 3 by 3 matrix now, but we also have a dependent current source in the mix. So to do that, basically we're going to do everything the same and apply our KCL method. And so I'm going to label everything as usual. and you can check that everything is consistent. The direction of current flow is consistent here. And we're going to go ahead and jump right into writing the equations. So we're going to have I is equal to Ix plus V1 minus V3 over R4. That is this current. And equation 2 is going to be relating to this node 2 here, and that's going to be Ix. Let's see, Ix is equal to V2 over R3 plus V2 minus V3 over R2. The third one's going to be again V2 minus V3 over R2, which is this current, plus this current is also adding into that node, which is V1 minus V3 over R4, and all of that equals this current coming out, which is 4Ix. Now let's look at how many variables we have. So we know that I has a source and it has a value to it, so we don't worry about that as a variable. We know that we're going to have 3 voltage variables, so we have 3 equations for those, but we also have a current variable Ix, so we also need an additional equation for that. So what we can do is say that our fourth equation is Ix is equal to V1 minus V2 over R1. And so if we plug this back into the rest of these equations, we would be able to obtain what we need to then plug into a matrix. Okay, so now that we've plugged in Ix into the previous 3 equations, we now have 3 equations that are only in terms of V1, V2, and V3, and some other known variables such as I and resistor values. And so now we can get everything into the matrix form, and to do that we're going to simplify everything in terms of the usual coefficient times variable plus then another coefficient times the second variable, and so on and so forth. So we're going to need this kind of form. So looking at the first term here, we're going to have, again using conductances, we're going to have G1 plus G4 times V1. Now for the second guy, we're going to have a negative G1, and for the third one, we're going to have a negative G4. Now moving on to the remaining equations, we're going to have 0 times, let's see, negative G1 for V1, plus for V2 we're going to have G3 plus G1 plus G2. So let's double check that, G1 plus G2. Just doing algebra very quickly, I recommend that you pause and try this yourself. And for the third one, we're going to have minus G2. Now the third equation, we're going to simplify everything in that term again, in that sense. So we're going to have V1, 4 of it over there. Okay, let's see. So we're going to have G4 minus 4 G1 times V1 plus V2 is going to be G2 plus 4 G1, and let's see, we have V3 left, and V3 is going to be minus G2 minus G4. So now I'm going to actually find the conductances and be able to find a nice numeric form for these matrices. And so let me go ahead and simplify everything on the next page for you. Okay, so plugging every number in and simplifying everything into the matrix form, we get this current source vector here, as well as the conductance matrix and the unknown voltage vector. And so Now that we have a 3x3 matrix, we're not going to keep doing it by hand anymore. We're going to just use MATLAB to solve these problems for us. And this pretty much simulates a real world environment where the larger the circuit gets, we basically let the computer do all of the work, and we simply sanity check the results and kind of carry things forward for the computer to do. Okay, so the results that we get for this vector, for these matrix equations, is that the voltage 1 is negative 25 volts, voltage 2 is negative 36.1 volt, and the third one is negative 82.3. Okay, so having verified that we performed all of the linear algebra steps correctly through MATLAB, we're now going to verify that we actually performed KCL correctly in our circuit and arrived at the correct equations to put into matrix form. To do that, we're going to use LT Spice to model our circuit, and as well as its dependent current source. So let's review. We have some current source here that's independent, a resistor network, as well as a dependent current source that for which its value is 4 times the current IX, and IX is the current through R1. So let's go ahead and actually see how we can model this in LT Spice. Okay, so before we talk about how to model the dependent current source, let's talk about direction of current. So in the schematic, you can see that I have the current pointing upwards, and here I have the current source pointing downwards, but I have a negative 5 amp value to account for the reversal in direction. So you can either have a downward pointing current source that has a negative value, or you can just simply go here and select the current source, and press Control R to rotate until you get to the cardinal orientation, and right click on the current source and select the positive value to correspond with the schematic. Either way, this should work. I'm going to save this, and I've applied a DC operating point simulation here. And the way you do that is, let me go ahead and delete this. I'm going to go to that moving hand and delete. Actually, you can just press on delete and click there. I'm going to go to run and click on DC operating point. Press OK. And we can of course see that we have negative 80, we have negative 25.3. Let's go ahead and go down here and compare side by side. It's kind of hard to see here. So negative 25 about 0.4, negative 36.1, and V3 is negative 82.3. So how do we actually model dependent sources? So in this case, I'm using a voltage source in the branch where IX flows, and I'm setting the voltage across that source to 0. Now you might be wondering, how come we're not using a current source here to since it's a current dependent current source on the right side here, bottom right side? Well, the issue with that is if I chose a current source here, independent current source, if I set the current value to 0, that means that I have an open circuit, so no current flows through that resistor. So the issue with the current source is that if I set a definitive value, I'm messing with my circuit now. I'm actually injecting a dependent or an independent current source value into that branch, and so that wouldn't work. So any value, if it's 0, it's going to open my circuit, because no 0 current through a current source means that it's an open circuit. And if I have any non-zero value, I'm actually injecting current into my circuit and messing up my the operating point of my circuit. So we use a voltage source to basically allow it to capture the current that's flowing through that branch. And what we do next is we use the dependent current source, which if I go to component and look for F, I see this symbol here. Then I right click on it and click on value, and what I do there is I'm using Vx. So Vx is the voltage across that voltage source that is set to 0, and I have a 4 here that is the multiplier, so 4 times the Ix is what I was looking for. Now, since I already have one, I'm going to cancel this, and I look here that I have a 0 value, and if you don't put 0 here, if you just leave it blank, the operating point operation is going to actually assume that you have a 0 there. And so that concludes our discussion about dependent current sources. One last thing I would mention is that the polarity also matters. So since we have a current flowing from V1 to V2 based on our assumption, if I actually flip this polarity, I would see that I would get very wildly different results. So just pay attention to your polarity based on your assumption, and ensure that it matches what you've assumed for your schematic. Okay, so now let's begin talking about the idea of supernodes. So what are supernodes? A supernode is formed when a branch in the circuit contains a voltage source of some kind, either dependent or independent. So why is that? Why does that have its own term? Why is that important? Well, if you recall, an ideal current source provides a specified current no matter what the voltage across its terminals is. Now, an ideal voltage source, independent voltage source, provides a certain voltage across the terminals no matter what the current through it is. And so the problem this brings forth to us is that we can't really, since we're using KCL for nodal analysis, we really don't know the current that flows through this voltage source. It could be any current that allows the circuitry inside of this voltage source symbol to provide 5 volts. Because recall, earlier in the video we saw that current sources and voltage sources are actually produced using transistors. And these transistors, a lot of variables inside of these transistors and around their circuitry is going to vary to provide some basically some sort of a parameter, voltage or current, from that module. And so in this case, this current could be whatever it needs to be for the circuit to be able to provide 5 volts across its terminals. The issue with that is it is not determinate. We do not know what it is, and therefore we call that a supernode. And somehow we need to develop a technique to kind of either bypass it or get rid of it so that we can get back to our business of solving these circuits. So the way we actually deal with that is we say, okay, we don't know what the current through this block is, the 5 volt voltage source is, but we do know that whatever it is going in, let's call it I, it is what's coming out. And so the basic idea is we don't know the quantity, but we do know that it's going to be the same current entering as it is exiting. So what we basically do is we, in terms of currents, we sort of ignore this branch. We sort of lump this whole, we crush this branch into a black hole, if you will, and we find some sort of substitution for the current I. What do I mean by that? What I mean is that when we determine our current direction, so I'll say this guy's going up, let's do it at the node so we know where it's going. Let's decide on this convention here, going up here, going down on this node. And let's actually give a name to our nodes, V1 and V2. And let's say that this guy's going this way. We already know I is going to the right, and I is going to the right here. And same thing there, going down and exiting there. So let's go ahead and actually write the equations for these two nodes. So for V1, we're going to say that it's going to be 3 amps entering, and that's going to equal I, which is exiting here, plus V1 minus V2 over 5, which is the current going this way, plus V1 over 4 ohms, which is this current. And for the second equation, we have I entering, and that's going to add to the other current entering, which is V1 minus V2 over 5, and that's going to equal what is exiting, which is V2 over 8 plus 10 amps. And so we know we have 2 unknowns and 2 variables here that we care about, we care to find. So in this case, V1 and V2, we do not know what they are, and also we have I. So we have 3 variables total and 2 equations. So the problem here is that we need to somehow eliminate I. Once we eliminate I by solving these equations, so essentially I take this guy to the other side and plug this into this I, or vice versa. The problem with that is once we do that, we've eliminated one equation, and now we have one equation and two variables, v1 and v2. So what we need is a third equation to basically be able to satisfy or solve the system of equations. So what we do for that is we invoke Kirchhoff's voltage law, or KVL, to be able to invoke some sort of physical law and solve the circuit. So how would you apply KVL here? Well, we know the likely loop of interest is KVL. Now, so we're going to talk loops, not nodes. The likely loop of interest here is this loop, and the reason for that is it relates V1, the problematic supernode voltage, and V2 all in one loop. And so if you go ahead and write that equation, let's see what we get. So I'm going to start at ground, go up. I'm going to see that the current's flowing from top to bottom on the 4 ohm resistor, so I assign this polarity plus minus. Before we go any further, let's go ahead and just do that for this guy too. So we're going to start from ground, which is 0 volts. I'm going to go up and see a negative sign, so a negative potential, and that's going to be a negative V1. Then I'm going to go up and see a negative 5 volts, and I'm going to go further and see a positive V2 here. Positive V2, and all of that is equal to 0. I take 5 to the other side and simplify, so I would get that 5 volts is equal to V2 minus V1. And if you look at this, this makes sense, because if I start from V1 and I look into this direction and go to V2, I see that I've risen by 5 volts. So in other words, if I'm sitting at V1 and I think of potentials as height, like gravitational potential, I see that as I go this way, I'm going to rise by 5 volts and reach V2. So essentially, this, for Kirchhoff's voltage law, this sort of provides us a constant voltage, and it's by law, by KVL, it becomes a constant. So whatever V1 is, V2 is going to be 5 volts higher, or vice versa. And so knowing this now, we can actually simplify everything. So let me go ahead and start from the beginning and actually obtain simplify equation 1 and eliminate I. So if I just rewrite the first equation here, now keep in mind that we usually don't simplify any of the coefficients in the matrix form until we're done with every single simplification, so that we can we don't have to do it multiple times, the cleaning up process for the matrix. So in this case, I'm going to take everything on this here to the other side. So I get I is equal to V2 over 8 plus 10 minus V1 plus V2 over 5. And the third one, let me just go ahead and write that. It's going to be 5 is equal to V2 minus V1. And let's go ahead and plug equation 2 into equation 1. And what we get now is, let's call this 1 star. It's a new equation. It's going to be 3 is equal to, and let's keep in mind that these are voltages, the units we should keep in mind. 3 amps is equal to V2 over 8 plus 10 amps. Let's see, right, so minus V1 plus V2 over 5. So that's just I. Now we're going to add the rest of these terms. V1 over 4. And for the second equation, which I will call 2 star, is going to now be, let me just go ahead and call it 3, because by identity it's just equation 3, and we already know that it is 5 volts now is equal to V2 minus V1. So I'll go ahead and simplify the first equation. Okay, so I've gone ahead and actually simplified these two equations. Now you may be wondering, okay, if I want to plug this into a matrix, I have an issue, and the issue is that for my sources, I have a current source and I have a voltage source. If you look here, I have an amperage and a voltage. And to solve this problem, we basically just simply multiply both sides of the first equation by 8. to eliminate the resistance, because recall that 4 and 8 are just resistance values and voltage over resistance is current. And so if you multiply both sides of the equation by the resistance value, the units work out in such a way that we have amps times ohms, which is voltage. So the top side essentially gets to match the bottom side in terms of units. And so if I just multiply both sides by 8, what I would then get is 1 star star, I will call it equation 1 star star, is going to be 7 times 8, negative number, negative 56, and then we're going to have 2 times V1 plus V2, and these are both voltages. And in this case, let's do negative 1 V1 plus 1 V2. Let's also put a 1 here. And so if you simplify this into the matrix form, we get negative 56, 5 is equal to 2, 1, negative 1, 1. Now let's go ahead and actually check this both in terms of if we did our algebra correctly, and the way we check that is we use LT-SPICE simulations, and let's see if we did our if we're going to do our matrix multiplication correctly, which we're going to just skip and directly do it in MATLAB. Okay, so checking our matrix algebra validity in MATLAB, we're going to simply input the matrix 2, 1, negative 1, 1, which I've placed there, and we're going to have our source input matrix as negative 56 and 5, which I have over here as I. In this case, it should be V just to stay consistent. Then I'm going to invert it and let's correct it. Then I'm going to invert it and multiply by, excuse me, I keep making this error, V. So if I now take a look at my results, I see that my output vector X is negative 20.33 volts and negative 15.33 volts. So if I then take a look at my LT-SPICE simulation, you can see that I have the correct values: 5 volts, 4, 8, 5, and 3 amps, 10 amps in the correct directions and the operating point. If I then one more point is that if you label your nodes, you'll have a much easier time decoding or deciphering what's going on in bigger circuits. So if I calculate this, I can see that V2 is negative 15 and V1 is negative 20, and this concludes our supernode example. Okay, so now let's go ahead and start taking the quiz. So in the first problem, we're asked to find the voltage Vout in the circuit. Now you do see 2 current sources. There's no super nodes because there's no voltage sources. So this should be somewhat or fairly easy to do. We know we're going to have 3 distinct voltages that we're going to have to assign. So we're going to have a 3 by 3 matrix that we're going to solve for. Now don't worry about Vout being a difficult issue, because once you solve for V1, V2, and V3 as we have before, you should be able to easily find the voltage at the across the resistor there with the polarity given. The next problem is to find voltages V1, V2, and V3 in the circuit below, and we can see here that we have voltage sources, independent and dependent, and this is going to form 2 separate super nodes. And so I would just advise you to pay careful attention to how to eliminate these variables. So I'm going to give you some time, and I expect that you pause the video and actually solve these problems to get the most out of this lecture. So assuming that you're actually giving it a try, I'm going to go ahead and solve the first problem. So to do the first problem, we do what we normally do for nodal analysis, which is I'm going to assign some node variables. And actually in this case, we have 4 different node voltages. Initially I said 3 different node voltages, so apologies if that confused you. Next we're going to assign the directions. So let me go ahead and do that in this color. I'll just assign this direction. just ensure that you stay consistent. No worries here that having all the currents come out, that should be no problem as long as everything is consistent. So I'm saying that the current's going, leaving that node, so I'm going to go this way. Now we're going to verify our directions, ensure that everything is consistent, and everything adds up. So let's go ahead and find the first equation, which is let's see, V1 over 3 plus 8 amps is going to equal V4 minus V1 over 10. The second equation, let me go ahead and write that up here so I have more space. The second equation is going to be for node 2, which is let's see, we're going to have 8 amps leaving, and let's see here, we should have V3 minus V2 over 5 ohms is going to equal the 8 amps and the V2 over 4 amps that are leaving. For node 3 we have all of the currents leaving, so V3 minus V2 over 5 ohms plus V3 over 4 plus 4 amps, all of that equals 0 because they're all leaving. And for the last one, we're going to have 4 amps equaling V4 over 3 plus V4 minus V1 over 10. Now let's add an additional equation here, which is the fact that V out is equal to simply let's see, V1 over V1 minus V4. So we have 5 equations there to eliminate V out, or to solve for V out. So I'm going to go ahead and simplify these on the bottom here and plug it into MATLAB and also show the LT-SPICE version to verify our answers. Okay, so prior to actually doing that, let me correct a mistake that I made. So for the first node, I essentially did not pay attention very carefully to where 8 amps should be. So if you look again, we see that 8 amps adds to the node, and V1 minus V4 over 10 ohms also adds, but V1 over the 3 ohm leaves. And so we can say that V1 over 3 is equal to the 8 amps plus the other current that's going to add. And what that's going to do is, once you simplify the equations, you're going to essentially get these equations, and I'm going to what I've done is I've put them into the matrix form, and this is what you get. And up to this point, you should be able to get the same answer as me, and that would indicate that you can do your algebra and nodal analysis correctly up to that point. Now, if you actually check the answers in MATLAB, you would see that these are your node voltages. And let me just briefly show you. You can see that my node voltages are given here, and what we really care about is the difference between V1 and V4, because as you can see, that indicates our output voltage. So V1 here, so that's equal to V1 minus V4, and calculating that, we get 7.5 volts. Now let's go ahead and look at LT-SPICE and verify our answer. Let me run it one more time. And of course we see that we have the same numbers as what MATLAB told us, indicating that we have the same answer. So that concludes the first quiz problem. Okay, so for the second quiz problem, we're going to apply all of the same principles. We're going to have a 3x3 matrix to deal with. And so what I'm going to do first is notice that for the first equation, I'm going to see that V1 is simply whatever V3 is plus 10 volts. We can see that because if I go to V3, I can see that if I go to the loop in this direction, I'm going to pick up 10 volts as I reach V1. So that's why I'm writing it like that. So that's our first equation. Our second equation is going to be based on our direction of current. So let's do that now. So I'll pick this direction, pick this direction of current and call it I. Pick this direction of current and call it, let's see, let's call this I1 and call this I2, and let's pick the remaining directions. That is of course I0 going to the bottom there. So looking at the first node, we have V1 over 8 ohms is going to equal the sum of these two currents, which are I2 and I1. Looking at the second node, we get, let's see, we get that V3 minus V2 over 4 ohms are going to equal, so this guy is going to equal the sum of the currents leaving. The third node is going to be, all of the currents are going to be leaving, so I0 plus V3 minus V2 over 4 plus whatever I1 is, that's going to equal 0. So let's also add a fifth equation, which is to eliminate the dependent voltage source here that is causing a supernode. So if I go around in this direction, what I would see is that, let's indicate the passive sign convention. So we're saying that the currents were going in this direction and we have to stay consistent. There's a voltage drop in that direction. So doing the loop analysis, we get negative. We're going to approach V1 from the negative side here, so that's going to be negative V1. We're going to approach the dependent source as from the positive side, so that's 6I, that's actually I0. 6I0, and then we're going to approach V2 from the positive direction, so that's V2, that's all equal to 0. So I'm going to go ahead and simplify the equations after stopping the video. Okay, prior to looking at the simplifications, there's one more equation that I did not write at the time. So the sixth equation is the current I out is equal to the voltage V3 over resistor 8 ohms. And so we have 6 equations, and we have to then find 3 equations that only have V1, V2, and V3, as well as some constants in the equation. So let's go ahead and actually simplify it. So for the first equation, it's very simple. We simply put everything in terms of the coefficient times V1, coefficient times V3, equal to some source value. Now, then we take equation 4 and we solve for I1, because remember we have to eliminate I1 and I2 as well as I0. So we solve equation 4 in terms of I1, and then we plug that into the equation number 2, and then by doing that we can solve for I2. Once we solve for I2 here in equation 2 star, we can then plug in the result for I2 into equation number 3. So by doing that, I have 3 star, and you can see all of the steps here. I won't bore you with them. And I then obtain equation, the final equation number 2 that I'm going to put into the matrix. And lastly, I look at the fourth equation and plug in what I found for I1 into the fourth equation. And so simplifying all of that, I get the third final equation that is circled. Now plugging those into the matrix, we obtain the following. So just following, so looking at the first equation, 10 volts is the source. So the source vector is going to be in terms of voltage. Then I have 1 times V1. There's no V2, so that's 0 times V2, which is here. And then negative 1 times V3. Negative 1 times V3. Looking at the second equation, I have a 0 as a source. 1/8, 1/2 times V2, 1/8 times V3. Then we have the last equation, which is 0 as a source, 1/6 times V1, negative 1/6 times V2, and negative 1/8 times negative 1/8 times V3. So plugging those into MATLAB, we get the following results. You get negative 6.67 volts, 5.83 volts, and negative 16.67 volts. I have the final answer written here. And finally, we're going to check LT Spice. Let me run it one more time. And before we do that, let's talk about what I did here. I used a source called H, and that is a voltage. That is a current dependent voltage source. And the way I'm putting the current in is I'm defining a voltage source that is of 0 volts along this branch to sort of measure the current through R3. And I'm using the variable name VO and multiplying by 6 to set the correct factor for the dependent source. And finally running a DC analysis to then find that these values are equal. So you can see negative 6.6, 5.83, and negative 16.66, which is what we have here. This concludes our lecture 10. I will see you in lecture 11 discussing mesh analysis, which relates to KVL. Thank you.